So thank you very much again for the invitation and to be here. And in this next short 30 minutes, I would like to give you a kind of overview about what we are doing and keep it very general. So I will avoid equations. I think there's going to be only one slide where there's going to be some equations, but mostly just about the concepts and what we are trying to do. And as Gergely already summarized, so that this is going to be something that how mathematical ideas that we are developing for almost 30 years are now pushed into high-level computer science, and then how it's going to be some products in the future. And as you can see, I'm also in Germany. I have a couple of affiliations also there, and Dynaplex is my company. So is there a pointer or right here? So I can. Okay, so usually the code that I'm developing is used by some 40 research groups worldwide for almost 2 decades. But now we also started to work on HPC and polarization. So there's a very strong collaboration in Stuttgart and also in Jülich in Germany, and in the US, this NERSC. And very recently, this Future of Computing Institute and this Renaissance Polytechnic Institute, RPI in the US. I will tell you what's the current story about this. And with industrial partners, we are having many collaborations in NVIDIA, AMD, IBM, Sandbox, so that's a Google startup, and with many other companies. And some of these already led to press releases. So there was one in 2024 with NVIDIA where we put the codes into the H100 nodes, and then we got out a very high performance rate, and that's NVIDIA recognized that's a big achievement, so that we had this kind of press release. And 2 months ago, there is a new one where we had calculations, this quantum simulation on the Blackwell hardware, which is a very new NVIDIA hardware. I will also talk about this, and how to decode FP64 arithmetics into integer 8 arithmetics, and how to utilize all these new recent hardware developments, so these other things. But before I go to the scientific parts, I would like to give you a little introductions about markets, because this is usually not the part of scientific talks. We are always talk about what we can do, how we do, what kind of problems we solve, but this concept of red ocean and blue ocean, I gave a talk for industrial investors some 2 weeks ago in a conference. And this concept is that when there is a technology which is very well known and all the market rules are known, and then basically that's what people call as a red ocean, because all the units and participants in this kind of market, they have a very strong competition. So it's a bloody competition, and that's why it's called red ocean. While if you have a new technology where even the rules are not known, the market is completely open, this is the so-called blue ocean, because you can do many things, and of course it's going to be dynamically set. And let's think about this little example that the transistor was invented in 1947. And if that time these 3 gentlemen would have said that transistor in everyday life, then maybe people would just think that these are crazy. I mean, there is some new stuff, but okay, that's nice. There was a huge, unit. And what about today? So that today we cannot live without transistors. I mean, even in our smartphone, we have more computational power than in Apollo 13. So it's amazing. And there was a shift from the blue ocean strategy to the red ocean, because at the beginning this was a blue ocean, but now it's a red ocean. So everybody is hunting, for all the improvements. There's a super big companies put a lot of money in that and so on. And nowadays we also have this kind of quantum effects-based units, and this is something like quantum computers. So that's again a new area, a new field, which we can think about the blue ocean, and that's why companies put a lot of money. That there is some quantum advantage that you can solve some problem with a quantum computer, which you cannot solve with today's present classical computers. Okay. So what kind of problems we want to solve? For example, in material science, high temperature superconductivity that we all would like to have. That it's a hot topic. It's under research for almost 50 years, and we still don't know how it works. And okay. The other thing is, for example, in nature, which is one of my favorite topics, is that how to fix the nitrogen from the atmospheric nitrogen and convert it to ammonia. The reason why we have 7 billion people in the Earth, because we have ammonia. Otherwise, we wouldn't be able to have this situation. But if there is in nature, there is one coenzyme which is responsible for this, and it's a very complicated structure. and has one open leg, a chemical bond, which is able to capture this. And if we would understand how this works, we could provide maybe a much better technology to do and generate ammonia, and that's going to be extremely beneficial for the whole society. Okay, now in labs, we can also form many complex systems, also in battery technology and so on. And all these are related that there is very strong correlations between the electrons. So these electrons are no longer independent particles, but they form new exotic states of matter. And this is exactly what quantum simulation and material science comes from. But the problem is that simulation of these problems scales exponentially on the classical computers. So if you increase and double the size, you need much more computational resources. And Feynman had this famous sentence, and the claim is that this would be also a polynomial on a quantum computer. And just imagine that in the classical world, we have the CAD program, so that we are building, designing ships, airplanes, buildings, without building the models every day. So it's a tremendous saving in cost just by using the computer simulation. Now, if we can do all the same thing with computers now for the quantum systems, then we can have also this kind of quantum CAD, okay? But the complexity of the problem, as I said, increases exponentially, so that the task is just as difficult as finding a given star in the universe. So this is an extremely complicated problem. But the good news is there are new mathematical algorithms developed in the past 20 years, which is called tensor factorization, where the exponential scaling can be brought down to the polynomial scaling, even on classical computer. And this is what I will focus on today. And this is the only slide that I put as equations, that just for experts, so that if you have a quantum many-body wave function, these are the components which is called this big tensor, which has as many legs, as many molecular orbitals or spins. And any high order tensor can be factorized as a product of lower order tensors. And this is what we see here. These are tensors with 3, 2 legs, and so on. And there are some mathematical description that these common indices, summations, these lines are the ones which represent it. But the take-home message is that this exponential increasing computational complexity can be brought down to a polynomial scaling, where the matrix ranks, the size of these matrices, are basically responsible that how accurate the solution and what is the system that we can study. And in physics, this is a big research for almost 20, 30 years. And there are many different tensor structures. So I don't want to get into details. And these are all have different features and useful for different systems. But what is amazing is also the same tensor structures appear now in machine learning and deep learning. So this is what is called now quantum-inspired AI. And this is also what we are pushing, where there's going to be, again, a very strong and big market. Because these are transparent networks, which current AI is based on brute force fitting functions. It's completely dirty in a way that we don't know what is going on. But these are transparent, explainable, and scalable, and can be fully polarized and also uses much lower energies. Plus, there's a very detailed mathematical structure behind that. So this is something that we hope on the long run that might replace current day AI, because the current AI models are not even scalable. For the next complex AI model, we don't have enough energy to feed this. So that's going to be something that we really have to work on, and that's a very hot topic. Now, the big question is that we develop all these things, and then at some point we also put new sensors, and all these AI will just interact with our world and what will happen, but I don't want to go in this direction at the moment, but just keep it in mind that the same framework is also in AI. So we have a mathematical algorithms, and all these tensor components can be processed independently, so it's an excellent for HPC, for high performance computing. And for example, one of these tensor network, which is called the DMRG, the dynamic DMRG, they use the full capacity of the K computer in Japan, and they get the Gordon Bell Award in 2012. And that time, this computer had 10 petaflops. Now, what is flops? So just everybody should blink once. Please do it. Okay, now in 1 second, try to blink twice. Okay, now try to blink 10. Does anybody achieve this in 1 second? No. Okay, so this imagine that we are not blinking 10 times, but 10 to the 15 times. Okay, so this is what is happening in a single second. So that's what we heard in the previous talks. It's amazing. And now in 2024, we already have the exaflops, which is 10 to the 18. Okay, and this was a super big computer in 2015, you know, very big rooms and everything. And now this is what we are working on. The NVIDIA Grace Blackwell 200 with NVL 72 technology. That means this is a super fast network. I'll tell you more detail. And from this single node, the supercomputer structures, you can get out this performance. So it's amazing. That's great. So we have the mathematics, we have the algorithms, we have the hardware, but no programs. So all the programs that has been developed in the past 20, 30 years are all Fortran or C++ revisions, but they are completely unable to utilize all these powers. And even if you take the NVIDIA CUDA, it's optimized and given only for single GPUs. There is no multi-GPU kernels, even from NVIDIA. So if you run your Python scripts, you can simply utilize single GPU. So now we developed the multi-GPU solutions, as I will tell you, but there's a major concept. So when you have millions of independent tasks, for example, that you want to do, you always need a kind of scheduler. And all algorithms currently work. There's a central guy who schedules everything because he's the one who can see the final mission. So there are some threads which are generating tasks. There are some which are responsible for moving it. And there are some executors like, you can have GPUs, FPGAs, CPUs, and so on. And of course, there are different communication channels. But the main problem is that if you increase the complexity of the task, there is more and more overhead on this central load balance or this central scheduler. So at some point, it's going to be the bottleneck because it cannot be handle all these things. And there can be some nodes or some units which are in idle. And therefore, this is not going to be scalable for these very high performance computing units. So with Andor, we replaced this guy with a so-called contractor, and that means that we have the CPU cores, the GPUs, and everything, and some are responsible for generating tasks, like what to do, matrix multiplications, and all these metadata. Everything is checked into some kind of Boolean flag, this contractor book. And all the executors and all the units which are responsible for transport go for this and check out, is there a task to do? And if yes, then is it a transport or it's an execution? And they start to do it immediately. And nobody is in idle because everyone is self-motivated. It's fully scalable. And also the number of units preparing the task or transforming or executing is fully adjustable. So everything is dynamically adapted. And if you just have more and more access to more computational units, it's fully scalable. Okay, so without getting into details, because we don't have time, this is the mathematical framework for this new mathematical parallelization. There is also an issue about memory management that if you have this lot of memory access, then even NVIDIA kernels are extremely slow. So that puts a lot of overhead in memory management. So we wrote our graph theory-based memory management functions. We just check out the GPU memory at the beginning, and then we use our in-house built kernels. There's also a way how to organize data into continuous segments into memory. So we also reorganize everything, and then we use this kind of strided batch operations, which means in a given operation, you can carry out hundreds or thousands of matrix multiplication just by a single batch call. And also, this is the kind of execution, this different hashing system that how to utilize these different executors. Okay. So without getting into the details, and before getting to the GPUs, we did this performance that how our parallelization work just on a single CPU node. And if we just increase the matrix sizes, which is the computational complexity of the problem, and we measure the performance in teraflops, let's say purple is the one which you get if you use Intel MKR parallelization thread. This one, the yellow, if you use OpenMP. And this is ours. And this was done on, let's say, correlating 18 electrons on 18 orbitals, which is the biggest problem that you can solve exactly on supercomputers. But here we can get this result in a few minutes instead of several hours. And also you can see this very fast increase in performance. And then here, the maximum of this Intel processor was 2.7 teraflops. So we'll be basically running our calculation at the maximum capacity. And this is already a very nice sign. And also, if you increase the system size and complexity, you get even a faster scaling. So we are able, with this method, to fully utilize the full capacity of the hardware. Also, I don't get into details, but you can do also symmetries and many other things. You also have to work out every single mathematical aspect in a way not to put overhead into the computation. So there are a lot of programs which can do many things, but nobody cares about that it runs for 5 minutes or 10 minutes or hours and so on. If you run millions of operations, it ends up for months and years. So it's very important. Okay, if you do this, we made some measurements on an A100 node. These are these blue ones. That's nice. Again, as a matrix ranks with the dotted lines. And this is the FP64 limit for 8 GPU cards. So this is already 8 GPU cards. This is not a single GPU. But NVIDIA also provides the so-called tensor core unit so that you can have a little bit higher performance, like 150 teraflops. And out of this, we get out 120. And even the best NVIDIA benchmark is 140, just full matrix multiplication. So NVIDIA said, oh, this is great. You solve the problem of multi-GPU, all the communication overhead, and then you get out this very high performance, and you are also utilizing the tensor cores. And that's why the press release came out 2 years ago. And then we switched to the H100, and therefore we can go up on a single node, we can get out quarter petaflops performance just from a single box, okay? Now, if you put together 40 of these, you get out the same performance as 2015 from the K computer in Japan. So just to see that what is the evolution of all this hardware and all these things, but you must work very hard to get it. What is nice, in this algorithm, the exponential scaling is brought down to polynomials, it's d to the cube. But as long as the performance increases so quickly, you measure the computational time, and then you get these very nice data sets on a log-log scale, which are linear, and then the exponent is 1. This means that as long as you increase the performance, you can bring down the exponent from 3 to 1. So we get a linear scaling, and this is why we can do now calculations within 1 day, which for others takes 3 to 4 weeks or even 2 months. Okay, so and the speed up compared to the single core is 10,000 speed up. And what data I show you, this is also speed up if you have a node with 128 cores, and then you take 80 of these without any communication overhead, you get the same performance. So from a single NVIDIA DGX H100 is equivalent to almost 200 or 80 or 100, 128 core nodes. So this is amazing, okay? We already have the multi-node version with Andor. This is the petaflops computing, but it's unpublished yet. Okay, the other issue is that, of course, we all have to pay the electricity bill, and just making all these estimates and calculations that what is the given performance per watts, if you use a CPU calculation or if you do the GPUs, we were able to show that you get a factor of 4 to 8 reduction in the energy consumption. And of course, this is a hot issue now because the price of the energy just goes up, as we all know. And even very new NVIDIA drivers like GB200s, there is also a further factor of 5 just from the hardware. That's great. And everybody in academia, we have access to HPCs. We are happy, and people are running the calculation. If you screw up something, then okay, we fix it next day, and then we rerun it. But in the industry, we pay $100 per hour on the Google Cloud, okay? So it's really cost. And Sandbox put me $50,000 on the Google Cloud. But then I realized that, oh, shoot. So that what we have to do also, that we have to identify the different algorithmic parts, whether it's better to put something on the CPU or whether to put it to the GPU. There are different communication channels like the SSD, the disk, the InfiniBand, the PCI Express, the NVLinks, and this is the bandwidth, as you can see. And even the double InfiniBand is 25 gigabyte per sec, while NVLink is 600 gigabyte per sec, and the current NVLink is 1.8 terabyte per sec. Okay, and this is what we are working on. But if you do all these things and then you cleverly adjust and organize your algorithm and rewrite it, the idea was that we check out one expensive node for $100 and some other parts of the algorithm we put onto CPU nodes, which we get out just for $1 or $2 or $3. And if you do this cleverly, then you can save almost $80 per hour. So that it's very important that besides physics and math, you really have to think about computer science and market as well. And also just a take-home message that current Boost libraries, which are used for MPI-based parallelization, are not scalable for these high-performance computing. Because data serialization is usually done in a single or 2 or 3 cores. It's completely unscalable. So with Andor, we rewrote also the data serialization protocols. I don't have time to get into details, but the take-home message is that we measure that as a function of the gigabyte of data, how much it takes to transfer the data. This is a double InfiniBand where the maximum is 25 gigabyte per sec, and this is where we are. And with our protocols, the data serialization and this serialization is completely hidden behind the application. So you really have to rewrite also current things. Okay, then there was a work, then NVIDIA, I have access to the NVIDIA newest kernels, and then I did some calculations on some emulation. I will tell you in a second, and NVIDIA found it so important that when they announced the Blackwell in Atlanta, the top 500 conference, they used our results, so it's good that we were represented also in such a big event. And the message is that if you have a Blackwell, GB200. Then to run calculations on FP64 arithmetics, it's about 90 teraflops per card. But if you go to int 8, it's 20,000 teraflops, okay? So NVIDIA would like to remove the FP64 units and put the int 8s because it's needed for AI. It's good. But for scientific calculations, int 8 is not enough. So that we really need for the general cases, maybe FP64 or something like that. So there is a new mathematical trick called the Ozaki scheme that you can split up the FP64 into slices. I don't have time to get into the details, but there's a mathematical way. You split up into slices, and then you do all the multiplications on int integer 8 units, and then you reconstruct your FP64. It's going to be an approximation like FP58, FP47, and so on. So how good is it? Nobody knows, okay? But the nice thing, this tensor network algorithm is variational. We have a full control about all the error bounds, everything, so that we can provide for the industry a hardcore tool also to validate their hardware, but they validate their approaches and everything. So this is a very big value in market. And so you can set now the monthly subits in the hardware, 15, 23, 55, 64, and so on. And then we did the calculations, and then we had also for this system results for exact solution with FE64. This is the blue one. And you can see that what is the error, how it drops down up to 10 to the minus 12 in this given problem. And if you use only approximation 6 or 4 or 3 slices, then you can see what is the achieved accuracy. And for 2 slices, which is the half precision, you get even non-variational results. So it's a complete crap. But there is a very, very, very serious way how to do all these things. That's nice. And we also work with IBM. And without getting into details, there is a Z2 Higgs high energy physics model, which you can map exactly to a hexagonal structure. And this is the hexagonal structure of the IBM Heron quantum computer. So then we did the simulation on some string baking and string evolution. These are the data points that you can see here. These are time measurements. The data points are on the hardware. And the solid lines are our tensor network simulations. And you can see this perfect agreement. Now, this paper is with Nature Physics. It's the second round on the referee reports. We are just replying to some questions from the referee. What is nice that we can go up to 70 qubits with perfect agreements, but TNS, we can go up to 200 without any problem. But the quantum hardware is very noisy, so that at the moment we can do much larger calculations, much more accurately, even on this 8 GPU card system. Okay, and recently, RIKEN and IBM has this quantum advantage tracker webpage, where they collect problems where they think that quantum advantage might be needed, okay? And they put this problem, this is some iron sulfur complex from chemistry, it's 54 electrons correlated on 36 orbitals, which is a 72 qubit system. And they put this on October, so that after Christmas, I said I had some time, okay, let's see. I talked to my friends at NVIDIA, and I did the calculation, and now it takes us for 8 hours on the GB200 hardware. So there is no need for quantum computer to solve it. And just because we can do it, I said, okay, let's provide them a new benchmark. So this is the new benchmark, this iron 5 sulfur 12, where you have 102 orbitals. That's basically 204 qubits. And we can do this. I think it's about 1 day, okay? And now this we can combine with some quantum chemistry codes where we can push the limits further with some approximation up to 400 orbitals, which is 900 qubits. So we are at this stage running on the Blackwell hardware, roughly speaking, 220, 250 teraflops. And just after this paper appeared, I got an invitation to give talk in Jülich, and I get access into the Jülich supercomputer to work on the GB200 and GB300. And a few days later, I got a mail from the director of the RPI, and then we had a meeting, and he offered me a full access to the 280 GPU cluster and quantum and Empire AI, which is going to be ready in a few months to 10,000. And Argonne National Lab is going to be ready end of 2027, 100,000 GB200. You imagine that I have shown everything for you for 8 GPU cards in a single node. This is already outperform all this quantum stuff. Now, from 8 going to 10,000 and 100,000, we are you know, for all these mathematical things and scaling, but the technology is around us. And this is just some scaling functions. I don't want to get into details, but the take-home message is that this made a big noise because now we are working on pushing all these algorithms on the Grace super chips. Also, AMD has the MI300 and 450 systems. But the big thing is that MPI has 25 gigabytes per sec bandwidth. This is the current parallelization. And NVLink is 1.8 terabyte bidirectional. Okay, so we gave up MPI-based developments. We are focusing on the NVLinks because it's going to be a dead end. And also this GB200 NVR70, it can connect 576 GPUs as a single NVLink domain, okay? With a 1.1 petabyte per sec total bandwidth, 240 terabytes of fast memory and so on. So this is amazing. And everything was developed because of AI, but just because we can use this kind of emulated mode, and we prove that it's also good for general scientific calculations, we can jump on the same train and take all the advantages that came out from the industrial developments in terms of this AI boosted technology. Okay, so this is what we are working on. And here I would like to close my talk and just to summarize that this tensor network algorithms provides a completely new mathematical framework to run the calculations on classical computers. And also, everything is ready for massive parallelization, multi-node, multi-GPU. It's towards exascale computation. Of course, energy demands are much lower. We can do simulation of realistic materials. Also, we are working on, I didn't have time, but we have this very special algorithms to decode everything in terms of 2-qubit gates in the tensor network so that it's a direct connection to quantum computing. We are working now with IBM estimating quantum circuit depths. I'm working with IBM at Zurich now on quantum simulations together. They don't want to write something on quantum advantage. They told me they are very interested about hybrid algorithms. So we are now working on this classical quantum hybrid algorithms because this is going to be the future. So classical algorithms will be needed. We are there because we are providing all the validations, and there will be a set of problems where quantum computers will be, of course, much better once they are stable. And the best thing is to combine all these things together. And that's what I'd like to say. That so we take tensor networks, we take HPC, we have the blue ocean strategy because the market is not known yet. And I think this is going to all lead to this kind of quantum CAD, which means that we can have the same kind of CAD system for quantum materials, systems, AI, and everything, because the same mathematical framework is useful for all these different topics. And here I would like to thank for your attention. And if you have questions, I'm very happy to answer.
Okay, thank you very much, Örs. This was a very nice and quick overview from the starting point of the academic perspective, how to go to the blue ocean. So time for questions. Tony.
Thank you. It was very nice talk. I would like to ask that your new algorithms, how accessible are for an everyday researcher like us?
It's closed at the moment because it's under, so in Germany, we are working on startup companies and also in collaboration with NVIDIA and IBM. So I got already some offers, but we would like to make it in a way that for academic use and then the industrial version. There's a quantum chemistry code which my code is interfaced to. This is the so-called ORCA code. I don't know if it's written here, but it's together with Frank Neser. He's the head of the Max Planck Institute in one of the Max Planck Institute in Germany, and they have the similar license, let's say, profile. And so my code is interfaced with that, so that people in chemistry working on this and making this professional, so that we have end user agreement, NDAs, and so on. But currently, everything is done through NDAs. Okay, so this is the RPI is also, for example, to sign all the NDAs. They are very happy, and then so this is the first step. But we would like to have it also for the general academic use, because everybody's looking for the code. Whenever I give a talk, I always get, can we get the code? And I said yes, soon, but okay.
Thanks, Örs. You mentioned this kind of translation from FP64 to int8, this algorithm, this method, but it looks to be an iterative method. So this raw performance difference between 90 teraflop and 20,000. So what is the actual experience with it? How much can you gain?
Yes, that's a very important question. I removed this slide because for 30 minutes, but I had one slide that here. This new cuBLAS library has a couple of settings that you can use. That means you can run an FP64 as long as there's an FP64 unit, and you can use these as a so-called performance mode where there is some heuristics that when to use FP64 and when to break it down to int8 based on matrix sizes and many things. And there is so-called eager mode where you enforce it and you really force only 15 multi-subits or 23, okay? So far, if you force it, it's much slower. If you use the performance mode, you get back to the similar time as you would use the FP64. But this was based on the so-called Ozaki 1 scheme. This is this kind of approximation. There is the Ozaki 2. We are working on the Ozaki 2 where you get a much bigger performance gain because the overhead to split it up into these integer 8 slices, run the calculation and rebuild it, that takes time. That's an overhead. And also here, you see that you have these matrices and that scales that number of slices, k times k plus 1. So basically this is k square where k are the number of slices, okay? But in the Ozaki 2, this is brought down back almost to k. So this is we are working on now the NVIDIA and showing that that all these approximations or this kind of it's called emulated FP64. You can use it in the same way.
Seems to be a preparation for the future. When I'm
exactly. So you're not going to lose performance. And also NVIDIA is providing some co-processor, let's call it co-processors, also to do this kind of splitting and all the algorithms. So I think this this is part of the big developments.
Okay, thanks.
Thank you. Further questions? We have time very fast, so maybe.
Oh, problem is that I didn't know that how much time. Okay.
Okay, so this is really amazing. And what do you expect when will these methods get up to, say, simulating proteins for the molecules?
Yes, this is something that
Really large molecules.
No, that's very important questions because we are also looking for the marketplaces so that we are working on the pitch for almost 2 years. So we are planning to have the fundraising in September. I told everybody that below 10 million euro, it doesn't make sense to start. And we really need 10 to 12 million euros. Otherwise, it's going to be, you can start something and it's going to be a dead end in 2 or 3 years because it takes so much effort. So with Merck, we are having some discussions. What are the use cases that they are exactly interested because that's basically the pharma industrial applications. I think that going from 8 GPUs to 576, there's going to be an order of magnitude increase. So that I think is already the stage where you can use these methods because everybody currently is relying on DFT, density functional theory, or couple cluster, that none of them are good for this kind of strongly correlated systems. People are using it because they don't have any other tool. So that's a handicap. And we all know that the results are crap, but this is the only thing that we can do. And now if you can use all these other things on the top of it and then refine, then you really get the accurate solution, especially for excited states. So that with IBM, we are working on excited states now because that's very important for the quantum computing aspects. Also that how you can target also the excited states because these are also very important in all these catalytic reactions and this protein-based research. Yep. So let's hope that we go up to 576. That's my first aim. And going from 500 to 10,000, that's going to be again something. So I have a lot of things already worked out, all these distributions and everything. The main problem is that I'm working on all these things together with Andor, my student, and the two of us. I mean, everybody's already amazed at what we did, but it's still. I mean, I need another 10 people just to work on this and also we need experts. I need somebody from AMD. I would need somebody from NVIDIA. So we really would need also the computation experts also.
Okay. Donny?
Thank you for the wonderful talk. At the end, you talked a little bit about classical computing versus quantum computing. So what is your timeline? Which will be the first year when quantum computing would beat GPUs on a useful applied physics problem like this chemistry application or something similar?
There is a big question about the matrix ranks. So all this, what I have shown you, these tensors has the non-zero elements, which is the matrix ranks, the size. As long as the given problem that we have is so-called not fully entangled, so you have a finite matrix rank, which is already good enough to get the given accuracy. I think tensor networks will beat quantum computing in this regime. There are theorems and talks that in nature, usually all these things which are around us lives in a tiny corner of the Hilbert space, which are responsible for this so-called moderately entangled systems. But if you have something fully entangled, then of course this is not going to be true. So the question is exactly here that in these simulations, for example, this is on a time scale from 1 to 4. That's everything is nice, but we can go from much larger time. I'm sorry, yeah, we can go also for much which you cannot do with the quantum hardware because of the noise. So that we can go up to 20. Now, if you make all these improvements in the quantum hardware, of course, step by step, that's going to also improve. There are also claims. I don't want to get this detail because that's not that I don't want to hurt anybody or say anything, but there are claims that these noisy quantum computers will be not the ones for the future. That's going to be a dead end. You need these fault-tolerant quantum computers and all these things, but then the technologies again, quite PsiQuantum. Every year they have a big announcement, but nothing is published or approved, and so that they are collecting millions of dollars from the investors all the time. So they are doing a very good, let's say, pitch in that sense, but nobody knows what's the output. Okay, so but definitely, in my opinion, this kind of hybrid algorithm, that's what I believe. So that you do something, you post-process the quantum data with the TNS, or you prepare the TNS inputs, the wave function ansatz for the quantum computer, or you estimate some quantum circuit designs and then just put it over there. So this kind of hybrid. But what is amazing that the next generation of NVIDIA, which is going to be Feynman at some point, that's going to be, I don't know, I just heard about it, what its capability, and then this Grace Blackwell is nothing for compared to that. So if this is going to be pushed like this, the big question is that at some point, the cards are larger and larger. So the Blackwell, for example, one card consumes 1,000 watts. So I'm using 10 kilowatts per hour just running this calculation. Even this is a factor of 8 less energy consumption compared to the CPU node, but still I'm using 10 kilowatts. I'm not paying for it because I got a dedicated node at NVIDIA. They put it together for me, so we don't have to pay the electricity. But now if you say that, okay, we can scale it up, but you use, I don't know, 100 kilowatts per hour, then that's going to be at the end, I think.
Thank you.
Remarks? I cannot see, but maybe I have a question. If
Sure.
Probably you can answer after this last verse. So what could be the real price from the market price? Because you said that the computational part is free for you, but if somebody really wants to do this on market level, so what could be the price for that?
Yeah, there's a Spanish company called Multiverse, which was founded, I think, 3 or 4 years ago. And this is the biggest one, which claims that they make these tensor network compressions on the LLMs. So there are these big LLM databases, and then they are making a compressions just with this, and then they claim that it's going to be much less computational complexity to do the interference and all these things. But I just learned that they are making, they raised $200 million just last year in the fundraising, but they are still having a deficit of 20 to 30 million euros per year, even that they do not pay for the computational cost because they have an agreement with Amazon that Amazon is investing into this company in a way that providing for free the computational resources. So at the moment, I think, for example, if you solve the high TC problem, I think you will be a billionaire and you paid, I don't know how many, you have to see that how much it costs, to run all the simulations. But imagine that you can solve all these very complex problems which you cannot do. And that's already a simulation, or you solve something in pharma industry. All metal-based problems in pharma industry is at the end. People cannot do this simulation. Now you provide all this, they don't have to build these expensive lab experiments. There is no chemically, everything you can do the simulation, then of course it's going to be a tremendous saving. So that this 10 kilowatts is maybe nothing in terms of cost than what it costs to do the experiments in the lab. I have a study yet, but that's basically the idea.
That's a very good point. Thank you very much. So I think we have to move on. So let's thank Örs again.
Thank you again. And